Welcome back to our data science course. As you can see here, today's topic is applications of the normal distribution. What we're doing is we're going to continue our calculations from last time with the bell curve and see how that plays out in word problems in applications. Now, a few programming notes as far as what I'm thinking as a teacher. I have been meaning to take out this old-fashioned practice of using the normal distribution table for a long time now because it's old fashioned and impractical. And this semester, I finally started to do that. This semester, as of this recording, is also the COVID-19 virus semester where we are teaching remotely with social distancing. So that's also going to affect a few lectures here. And thus, I want to apologize in advance. This is going to be a quick lecture to get to give my students a tutorial video of how to handle some of these calculations. But admittedly, it's not nearly as hands-on or illuminating as I would hope it would be. So what we're going to do now is with word problems, we're going to try to find the area under the curve, under the normal curve. And part of what happens in the background is that we're going to use our z-score formula that you can see here in the middle of the page. What happens is that depending on the word problem, we have a different bell curve. There are different shapes of bell curves. They're either stretched out or compressed inwards. They can move left or right. So in theory, there are infinity bell curves out there. To make the calculations practical, we do what's called a transformation and bring us right back to the standard normal distribution that we were studying last time, where the mean is z equals 0 and most of the data falls between -2 and +2 standard deviations. And that's what this formula does. It does that transformation to move the graph left or right, stretch or shrink, to bring us back to where a computer could help us finish the calculations in a practical way. So what I have for you right now is an example that I wrote 6 years ago, but it's oddly pertinent. Reading off the example, suppose that the incubation period, that is the time between being infected with the virus and showing symptoms, for the Ebola virus is normally distributed with mean 12 days and a standard deviation of 4.5 days. We're going to find the probability that a randomly selected case demonstrated symptoms in fewer than 7 days. So the way the z-score calculation would go sorry, no bit of typos here, is we'll write out the z-score to refresh memory how that calculation plays out. So as you can see in the word problem, if nothing else, I have mu labeled as 12, sigma labeled as 4.5, and thus by process of elimination, x would be 7. So what would happen with the z-score is that we would get a z-score of approximately 0.2083. Now, looking at the task at hand, I want to figure out the probability that the incubation period is fewer than 7. Now, the way we write this out in math speak is, for mathematically nerdy reasons, we usually write the unknown as a capital X. The reason why we write it as a capital letter is because mathematicians like to use capital letters for probabilistic situations where there might be some randomness involved. Fewer than 7 is written as usual as this inequality here, less than 7. And due to that mumbo jumbo I said at the beginning about transforming bell curves, we would get this number here. And chat is informing me that I have a typo, so I thank chat for that. Let me fix that. I switched the 12 and 4.5. Which means that this number we get for the z-score has also changed. So again, thank you for pointing out that typo. So we get a z-score of about negative 1.11. Let me see if I could move this text over a little bit. So that I could show you a diagram of what's going on. Continuing or adapting some of the code that we were working with last time. Here I have the normal distribution, but I have it shifted for the word problem itself, where the average incubation period was 12 days. So this peak, this maximum, is at x equals 12. It should say x there. At x equals 12. And we're asking about the probability that the incubation period will be less than 7 days. So here at x equals 7, we do the shading towards the left for less than. And what we're doing on the probability side of things is to figure out the percentage of area that this blue area represents compared to the gray area in total. And to do that, fortunately in R, we have a command for that called pnorm. Now, if we already had computed the z-score, all we would have to do is type in that z-score and get an area of about 13%. However, since we're going to be doing these calculations on the computer side of things, it's usually easier to type in the numbers directly. There's a bit of a rounding error from in the first number compared to the second number I computed. The second one is actually more accurate. But as you can see, what I did was I typed in x equals 7, the mean was 12, and the standard deviation was 4.5. So from start to finish, with the Ebola virus, on average, susceptible people would show symptoms on at 12 days. When I ask the question, what's the probability that they would show symptoms in fewer than 7 days, you could get a sense that's already improbable, and the probability was down to about 13%. Thus, for the Ebola virus, self quarantine for 1 week was not quite enough. And for the present day COVID 19 virus, that's why they recommend a self quarantine of 2 weeks. I'll go ahead and pause here and see if there's any questions from the folks in chat. What I have for the rest of the hour today are three more examples. That is, depending on the way the word problem or the task is presented, the calculations will be carried out in a similar way, but there might be one or two extra steps. So we'll see how that goes. All right, here in the second example, I said that Girl Scout Thin Mint cookies have a mean size of 0.25 ounces. We're going to find the probability that one randomly selected cookie has a size more than 0.27 ounces if the standard deviation is 0.03. And we're going to assume a normal distribution. I know, right? All my examples seem to be about food. So to parse the word problem a bit towards the formulas that we have looked at in the past, we have that mu equals 0.25, sigma equals 0.03, leaving the 0.27 for x. So now what I'm asking in context of the word problem is what's the probability that the cookie is unusually large? The mean was 0.25. I'm asking what's the probability the cookie is larger than 0.227 ounces? Well, that depends on how large the cookies are tend to be in the first place, and also how much of can the cookies be different from each other. That's what the standard deviation says. How much variance? How much can the weight vary? In the previous problem, we saw that the shading in the graph goes towards the left. And I want to keep an emphasis on that we usually place the shading towards the left, and usually the inequality is facing this way to say less than. So whenever we need to switch the directions of the inequality in a probability question, we will take the complement. Now, I said at the beginning that I'm changing the way that I'm asking students to carry out these calculations, both to avoid a very old fashioned way and also because we are all in separate locations at the moment. I'm going to kick up the difficulty a bit. Suffice to say, there is a function out there called phi. I'm going to label this Greek letter phi. And what we're going to plug into that Greek letter phi, I'll have it on the screen in just a bit, is the z-score conversion, the subtract the mean and divide by the standard deviation that we would have done anyways. Again, what capital phi does is it's a way to represent that we want to calculate the probability, that area under the curve. That will be the blue shaded area when I bring up the diagram. But again, I want to emphasize that in order to use this phi function, the inequality has to be facing this way, less than. Because the original setting had a greater than, we flip the inequality with the complement 1 minus. When we do the calculation in R, we also need to incorporate the 1 minus as well. So let me go ahead and see if I could draw a diagram for you. So this is what the situation looks like. We have an average Girl Scout cookie, Thin Mints in particular, with a weight of 0.25 ounces in the middle. And I'm asking for unusually large cookies, so the shading for greater than 0.27 will be shaded towards the right. And once again, the picture says that we're going to try to find the percentage of area, the blue divided by the entire area under the curve. So now, with that in mind, the way we type that into R is, again, with the p-norm function, but because we're shading towards the right, we need to incorporate the complement 1 minus somewhere. You'll also notice as I typed out those numbers, I did not have to say mean equals 0.25 or SD equals 0.03. As long as you type the numbers in the correct order, the software will understand what you're doing here. So we get a probability of about 25%. I'll take a pause here and see if there's any questions from those in chat. All right, for the third example, I'm bringing this one in from physics. The cones in the eye detect light. The absorption rate in cones is normally distributed. In particular, the green cones, that is the cones in your eyeball that detect green wavelengths of light, have a mean of 535 nanometers and a standard deviation of 65 nanometers. If an incoming ray of light has wavelengths between 550 and 575 nanometers, we'll want to calculate the percentage of that ray of light that will be absorbed by the green cones. So the signal word this time around, instead of saying less than or greater than, the signal word this time around is between. Whatever we're examining is in between 550 and 575. So you could see that's how I wrote the inequality down here. Our unknown is in between 550 and 575. Now, part of the process to bringing this back to the bell curve is to actually reduce the complexity of this problem by separating this into two separate calculations. And you can see the minus sign in between. Now, because we're talking about areas under the curve, we'll wrap up that concept of area under the curve in this phi function. Inside each one of these, we're essentially plugging in the z-score calculation. So notice that I'm bringing in what the average wavelength was and the standard deviation as well. Sorry, I have a typo there. So in the top left corners, I have the 575 and the 550 still. And like before, let me bring up an example diagram. So we're looking at this bell curve, and for all that stuff I said about physics at the beginning, we're looking at for rays of light with particular wavelengths in this sliver here that I have represented by the blue shaded region. And then otherwise asking what is the probability of being in that blue shaded region as opposed to anywhere else under the bell curve. We're using the p-norm command for our convenience and in calculating this. But as implied by what we saw with what I had written on the page, we need to do two of these calculations and put a subtraction sign in between. So, as far as me being the teacher is concerned, what I'm challenging my students this semester to do is for a word problem like this to be able to write down a similar set of calculations depending on the word problem. And finally, get this last number by typing in the appropriate calculations into RStudio. Alright, so let's try out one more example, one more setting. Reading off the example. Suppose that the number of french fries in the batches at In-N-Out are normally distributed with a mean of 42 french fries and a standard deviation of 37 french fries. Your friend tells you that the In-N-Out employee is flirting with you if you end up with a french fry count in the top 5%. How should we characterize the top 5% of french fries? The question in chat is, can we only calculate this through RStudio? And loosely speaking, the answer is yes. The proper way to calculate this would be with calculus integrals, and even then, the integral would take several minutes to compute. And thus, for any practical purposes, we would use a shortcut somewhere, anyways. And this semester, I am asking my students to type in those pnorm commands into RStudio. Whoops, typed that in the wrong place. So to parse some of the information, we have that the average mu is 42 french fries. The standard deviation, sigma, is 3.7 french fries. Now, the way I've set this problem up is we want the probability to be the top 5%, or the probability is at 95%, depending on your point of view. And thus, oddly enough, considering the formula that we have in front of us, the z-score formula, what's missing is our x value. And that's kind of what we're solving for. Give me a minute to bring this all up. So the way this starts to look at like mathematically is that we have our z-score conversion, and we want the result to be in the top 5%. So above the 95th percentile. Perhaps I should type that out as a sentence. So we want the result to be above the 95th percentile, and that's kind of why I wrote this z sub 0.95 here. Now, where we were finishing up last time was to handle this situation, these types of situations. And when we have this, where we have the probability, but we're going backwards to find the x value, this was called a quantile. And the way we type this into RStudio is with the qnorm command, Q for quantile. Otherwise, we type in our mean of 42 french fries and our standard deviation of 3.7 french fries as usual. And I apologize, I had the inequality going in the wrong direction. So we take the number that we get from the qnorm function and place it there in the strangest part where I had the z sub 0.95. But fortunately, now that we've dissected the problem and set everything else up, the the rest is solving an inequality. Sorry, I got ahead of myself here. As you can see on the screen, what I meant to type in the beginning was just the qnorm function with the 0.95. And then that number, the 48 point something. That's actually what we get for x. So again, when I did that qnorm function with the original mean and standard deviation from the word problem, that actually finished the entire calculation. From start to finish, at in and out, you know you have an unusual amount of french fries if you get at least 48 french fries in your batch. Let me try to move everything to a convenient spot, if possible. This was the last example. All right. I don't know if it was obvious, but that's well, it's kind of an awkward lecture. Nevertheless, my goal for today was to present you 4 different word problems to show you how this calculations change somewhat for those 4 different settings. We will definitely practice this in the upcoming week, but all I have to say at the moment is thank you all for showing up to this online lecture. I'm going to stop the record button and say, have a nice weekend.